Hi everybody. This is going to be about section 4.5. The title of this is actually different from what I've written down. It says direct proof and counterexample 5, division into cases and the quotient remainder theorem, which emphasizes one of the places where we'll do division into cases, but there are a couple of others. So the granddaddy of all division into cases things is dividing things up based on even and odd. If you do even and odd, what you're talking about is two cases. Then there's the thing they mentioned in the official title of the section, the quotient remainder theorem. Hope you don't mind if I just abbreviate that as the QR theorem. That will divide us up into quite a lot of cases. It basically divides you up into as many cases as there are potential remainders. Let's just say many. For now, I am okay, good enough. But there's other options too. There's a particularly nice thing that's called the trichotomy property of the real numbers, which I like to mention the etymology of words. Tri, this part right here, I think everybody knows that means three, and chotomy, the rest of that means cuts or divisions. Let's go with cuts. It has to do with knives in Greek. Anyway, trichotomy is cutting something up into three parts. And so you may imagine that means there's going to be three cases. This is easier than it sounds. It's just, I mean, it's got a fancy name, but what it means is every real number is either positive or it's negative, or it could be zero. There's those three options. Well, this isn't really a way to do division into cases, but an example of using division into cases that we're going to see at the end is a thing called the triangle inequality, which is simplistic, but it actually has quite a lot of depth to it. You see it used in proving other things all the time. So we'll close out by talking about that. So what is division into cases about? I think it's easiest if you think about the first type, even and odd. Suppose I were to tell you that every number squared is either a multiple of 4 or it's 1 away from a multiple of 4. It's 4k or 4k plus 1. Well, a quick way to argue that is, yeah, if you have an even number, it'll look like 2m. You square it, you'll get 4m squared. Yeah, that's a multiple of 4. If you have an odd number, well, you got to go through the algebra on that, but then you'll get a multiple of 4 plus 1. So you can divide things up into even and odd and prove a general result by saying, well, it's either one or the other. The cases have to be, well, like even and odd are. There's no overlap between them, right? There's no numbers that are both even and odd, but also they sort of cover every possibility. You're either even or you're odd. There's no third option. So your cases have to be exhaustive and disjoint. Let's get into talking about the quotient remainder theorem, because that is sort of what they use most in the book here. So I wrote it down while the camera was off, and so that you wouldn't have to watch me writing this whole thing down, but let's read through it together. So the quotient remainder theorem is the thing that is stated next. It's universally quantified over two variables, n and d, and you should think of those as numerator and denominator. It's really about a fraction, or the number and the divisor. But those are integers. Right? Now, this is a symbol we haven't seen before, or maybe we have. I forget. But putting an exclamation point after the existence quantifier says that the thing that exists is uniquely determined. So you read this, for all n and d and z, there's a unique pair of integers, q and r and z, such that. And then, well, what does it say? N is equal to q times d plus r. Now, the way I usually think about this is if I was literally doing the division, do the n divided by d, you're going to get the quotient plus a little bit, plus the remainder divided by d. And what do we got to do to turn this form into that? Just multiply through by d. Right? So that multiplying everything by d will knock out that d, it will knock out that d, and it'll add an extra d on the q. Why is this preferable to this? Because all the things that we're dealing with are quantified over the integers. And if I start doing things like this, I've left the realm of integers. I'm talking about fractions or rational numbers now. So while this is the way I usually think about it, do the division, get the quotient, and then you get a little extra from whatever remainder is left over. It's really better to write it this way in terms of when we're doing proofs, because you will definitely still be in the world of integers there. It's only multiplying, no dividing. It's kind of a smart thing to do if you've got a situation that involves division, but you can express the same thing without division. Well, that's better. Division leads to us leaving the integers for the rationals. All right, so what's so useful about this? Oh wait, I didn't finish the last part, because this is what's so useful about this. The final proviso is, in fact, without this, you wouldn't have the uniqueness. R has to be somewhere between 0 and d, and it can be equal to 0, but it's going to be strictly less than d. Why? If R was equal to d, then we just didn't make our q big enough. It really means q should have been q plus 1, and then R would be 0. So less than the divisor and positive, well, non-negative. Bigger than or equal to 0, less than the divisor. And what does that tell you? If R is an integer, and it's in this finite range, there's only a finite number of possibilities for R. This is not part of the theorem. I just want to point it out to you. The possible values for R, that's a finite collection. It can be in 0, 1, 2, ... all the way up to d minus 1. So how many numbers are there in a list that starts at 0 and ends at d minus 1? There's actually d of them, d numbers like that. So if we use the quotient remainder theorem, this is what we'll take advantage of, that the remainders are in one of these possibilities, right? And they're only d of them. So you have d cases that completely cover all the possibilities and that don't overlap with one another. Why? Because, if I have a number that leaves a remainder 1 and another number that leaves a remainder 2, I'm saying that weird. We got to talk about two different issues: disjointness and then exhaustiveness. So if I had two numbers that one had remainder 1 and one had remainder 2, is it possible they were the same? Is it conceivable we'd have one number that gave us both a remainder of 1 and a remainder of 2? That sounds a little fishy to me. I mean, if you actually carry out the process of doing multivision, you actually find out what Q and R do, and it's a mechanical process. You're not going to get two different answers at the end. So given any number n and divisor d, numerator n and denominator d, run through the division algorithm and figure out what Q and R are, and you'll have just d possibilities, but you'll never have n might be 1 or it might be 7 when you take its remainder. I just realized I used a word just now, the division algorithm, that we did look at earlier in the book. It was in chapter 1, I think, but it's just really a slip of the tongue, because the quotient remainder theorem is often called by number theorists the division algorithm. The uniqueness of Q and R from all this is a consequence of the algorithm. Anyway, usually what I think of when I say the word division algorithm is this process. You remember doing this in probably elementary school where you have like a number here and a divisor there, and you go 5 doesn't go into 3, but it goes into 30. It goes 6 times into 30, and you get and then, oh, that's a remainder because it's smaller than the divisor. Right? So that process we run through with this little L-shaped thing and a procedure you're all very familiar with, that's the division algorithm. Well, if you have a couple of numbers in mind, so I want to talk about some notation for the numbers Q and R that we'll discover. So given N and D, there's a notation for Q, which is this. It's called N, the word div written out, D, N div D, that's Q. And if you do N and the word MOD, mod D, that'll be R. If you've done, I think most everybody has learned Python, so I'll mention that the way to get Q or N div D in Python is to write N and then 2 division signs ND. And the way to get N mod D, or the remainder, is to use a percent sign in between N and D. So if you talk to old school programmers, they hit that and they just read N mod D. They don't say percent, they say N mod D when they see that. That's a very Pythonic kind of notation. Most languages don't do that, don't have a special symbol for N mod D, N div D. They would just take they would just take N over D, which would be a floating point number, and cast it to an int. And then that just cuts off this stuff after the decimal point. So that's another way to get at N div D. But yeah, you guys all know Python, so those things should be familiar to you. I'll tell you, in math, this one hardly gets used, but this one gets used all the time because R is the thing in this quotient remainder theorem that has this finitely many possibilities for it, just everything from 0 to D minus 1. So this mathematical notation for R is used all the time in order to get at the same kind of cases we're talking about for the quotient remainder theorem. Well, I think it might be useful just to take a second and show you how to compute some of these things, in particular the mods. So for instance, suppose it's 9 o'clock right now, and I want to know what time is it going to be 8 hours from now. And 9 plus 8, of course, I can add 9 and 8 and I get 17, which is not useful because clock time, unless you're in the military, only goes on a cycle of length 12. So what you need to do to compute this in civilian life is to write 9 plus 8 mod 12. Oh, I put parentheses around it. There are times when you need the parentheses and other times when you don't, and this is not really one of them. So let's just say 9 plus 8, 17 mod 12. Yeah, what is 17 mod 12? Well, you could just say, all right, I've got to set up the division problem where 12 goes into 17. And it goes in once, and I do 1 times 12, and then I subtract, and there's the remainder, 5. So the value of 17 mod 12 is 5. But that's often way too much work to actually set up and do the division. So let me give you another one of these problems, not with a story behind it, but if we just did like 73 mod 12. I'm just doing this one to illustrate that you can often figure out what a mod value is without having to do that. The reason for this is I guess it's because of the English system of measure, we're all pretty good with multiples of 12. You know, a foot is 12 inches, right? So 2 feet is 24 inches, 3 feet, a yard is 36 inches. If somebody's 5 feet tall, do you know how many inches tall they are? 60. 5 times 12 is 60. And if somebody's 6 feet tall, how many inches tall are they? 72. This is one bigger than a multiple of 12. Right? That's 73 is 72 plus 1. So if I know a nearby multiple of 12, and I realize that I just have to go up 1 to get to it, I know what the remainder is. This is 1. And it turns out there's a lot of numerical tricks you can do that help with that. Spotting nearby multiples of the modulus, they call that, the D, is very useful. Oh, right. I should point out a way to do this using a calculator. All right. So suppose we're trying to figure out, I don't know, 147 mod 11. 147 mod 11. Let's just do the division here. 147 mod 11 is 13.36363636, right? Well, you're already looking at n div d. N div d is the 13. How do you get at n mod d? Well, it's hiding here in the decimals. So what you need to do is just take away the whole number part of that and get just the decimal part, and then multiply this by 11, because that decimal that we're looking at there, that's really the remainder divided by 11. So if I times this by 11, I get a whole number. So in this case, let's return to the board. I was able to tell you that, gosh, what were the numbers again? 147 div 11 was 13, and 147 mod 11 was 4. It's a nice way to use a calculator to get it. Now, there's also actually a way to get the div and mod operators on one of these TI calculators, but what I just did, you could do on any calculator. Even with just a 4-function thing that has just adding, subtracting, multiplying, dividing, that would be enough. So this is the first theorem that they prove using the method of cases, division into cases in the book. It says the square of any odd number is of the form aq plus 1 for some integer q. One thing we should get in the habit of when looking at a theorem, before you just launch into trying to prove it, check it out a little bit and make sure that it indeed is true, right? So let's call n the odd number, and we'll figure out what n squared is, and then we'll try to write it in the form aq plus 1. So there'll be 3 columns here. Only odd numbers though, right? So 1 is odd, and then 1 squared is 1. Okay, that one's easy because it's 8 times 0 plus 1. If n is 3, then 3 squared is 9, and that is 8 times 1 plus 1. So far, so good. If n is 5, then you get 25 for the square. You got to know your times 8 tables pretty well for this. You recognize 24 as being 3 times 8. So 8 times 3 plus 1 gives you 25. At 7, we're at 49. Is 48 really a multiple of 8? Yes, it is. It's 8 times 6. Well, I'm starting to believe it. In fact, it's interesting what these numbers are. 0, 1, 3, 6. I don't know if you've spotted those before. Those are called triangular numbers. I don't know why they just happen to show up in this. Well, maybe I do, but anyway, triangular numbers are numbers that can be expressed as a triangular array of dots. So you could call that a triangular array, although it's, just a 1 by 1 triangle. But if you have 3, you can put it into a triangular array like that. And if you have 6, like that as a triangular array. The next triangle number would be 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. That's interesting because what's our next formula with the odd numbers? It would be n is 9, n squared is 81. Oh yeah, isn't that 8 times 10 plus 1? So, there's more to this than just that it's a multiple of 8. It's 8 times a triangle number plus 1, but that's all we need. Q here is going to be a triangular number. All right, I guess I'm convinced. I tried it out for a few examples and it seemed to work. Now what happens next usually is we make an attempt to prove the thing by cases, and we usually don't pick the right cases from the get-go. So in the book, they just sort of magically notice the right thing to use as the cases, but let me sort of model for you what a first proof might look like, and one that we would then later go and refine and make it a little nicer. What's obvious for cases is the form of this thing, where it looks like AQ plus 1. So why not use the possible remainders on division by 8? All right, so let's start a proof by saying, well, there are 8 cases to consider based on the value of n mod 8. Many of them we will not have to worry about, because if I take a number n and divide it by 8 and I end up with an even remainder, that's going to mean that the number was even. So we could include all 8 cases, or you could put something up front, which is what I'm planning to do, that says the cases where n mod 8 is 0, 2, 4, or 6 are even numbers. What's the best way to say this? The cases are irrelevant, really, because those numbers will give us even, will correspond to even end. So what we're going to need to look at are the individual cases where n mod 8 is 1 or 3 or 5 or 7, the odd numbers that are amongst the remainders. No, shoot, I just wrote that wrong. It's supposed to be 1, 3, 5, and 7. I was just worried about how much space I had left, so I tried to write the wrong thing. So the way of division by cases proof is going to work is usually like this. There'll be some little preamble that sort of spells out what the cases are. And if they come from the quotient remainder theorem, the way these two, you don't have to worry about mentioning that the cases are exhaustive and disjoint from one another. That's well understood. But if you're using something besides quotient remainder theorem and you still think that you've got cases, this is where you might try to argue that your cases are exhaustive and disjoint. Anyway, after that preamble, you're going to have some kind of a bold thing that says, here's the first case. And this is going to be the case where n mod 8 is equal to 1. I usually just put in parentheses what's going on in the case we're talking about. But what this means is that since n mod 8 is equal to 1, in this case it is anyway, that means that by the quotient remainder theorem, n looks like 8 times something plus 1. Where k is some integer. What I want to have happen in each of these cases is that we get to the result we're after. So that's what the work is going to be. I'm going to take the form that we've just discovered for n. It looks like 8k plus 1. In this case, anyway, it does. And I'm going to figure out what n squared is. Oh, that's tough. That is going to be 64k squared up front. And then there's outer times outer is 8k, but inner times inner is also 8k, so you get this k squared. 16k, those, and finally plus 1 on the end. Now, remember what our goal is. We want, in fact, we want to have n squared look the same way. And it does, because this can be re-expressed as 8 times something plus 1. What's the something going to be? Well, 8k squared plus 2k. So there you go. We've put it in the form that we desired. So that q is 8k squared plus 2k. So that case is dealt with, but we've got to do the remaining cases. And sometimes this gets tedious, and this is going to be one of those times. A lot of times when that's the case, you say the remaining cases proceed similarly. But I'm not going to do a cheat like that on you guys right now. We're just going to roll through this and do all 4 of these cases. All right, case number 2. That is when n mod 8 is equal to 3. I will try to abbreviate some stuff, and we don't have to do the since n mod 8 is equal to 3, but again, let's just say by the QR theorem, that's pretty decent abbreviating too. And the QR theorem, n is equal to 8k plus 3 for some integer k. Now, I think I got you guys all trained to not use the same letter for 2 different things. Right? So did some of you just instinctively go, oh shoot, he's using k again, we used k back here, you can't do that? that's good if you felt that way, but this is an exception. When you're in a proof by cases, the cases are independent of each other. So if you use the same letter again in a different case, it's fine. This is one spot where reuse of a letter is allowed. You think of these as different threads for a processor. They can be using the same variable name in the threads, and each one is actually referring to a different spot in memory. So yeah, it's all good. All right, so didn't finish my sentence. N is equal to 8k plus 3. All right. Just getting rid of everything but the start of the case that we did. Where do we go from there? Well, n squared is equal to 8k plus 3 squared, which is equal to 64k squared first. Outer times outer is 24k. Inner times inner is also 24k. That's 48k. And then there's a plus 9. Oh man, that looks bad because we're trying to end up with it being something, 8 times something plus 1. And we've got a plus 9 on the end. But it's not as bad as all that. Think of the 9 there as being 8 plus 1. And then you can re-express this whole thing as 8 times stuff plus 1. It'll be 8k squared plus 6k plus a 1, and then plus a 1. That's the 8 and that's the 1, so you get 9 out of the total. But did I do this all right? 8 times 6 would be 48k. 8 times 8 is 64k squared. Awesome, yeah. So again, the result works in this scenario. Case 3, that's where n mod 8 is 5. So by the quotient remainder theorem, n is of the form 8k plus 5. Fine. 8k plus 5. Well, let's do it. N squared is going to be equal to, let's write it first, 8k plus 5 squared, which is 64k squared, plus 40 and another 40, that's 80k. And 5 times 5 are 25. Now again, we have to end up really with a plus 1 on the end, so let's, at least in our minds, we should be thinking of this 25 on the end as a 24 plus another 1. Then you can rearrange it the way we want it to be. It's 8 times some number plus 1, where the sum number is 8k squared plus 10k plus 3. And finally, case 4. This is where n mod, do that again. N mod 8 is equal to 7. And here, you're going to again use the quotient remainder theorem. To write n as 8 times something plus 7 in this case. let's see, we'll keep the beginning of case 4 at the bottom of the board so you can follow along. We'll get rid of all the rest of this stuff. We're almost done with the last of the cases, and then there's just one last little segment, usually a wrap-up paragraph that we'll need to write. So, by the quotient remainder theorem, n is 8k plus 7 for some integer k, all good. Then n squared, well, it'll be 8k plus 7 squared, which is 64k squared. 7 times 8 is 56, right? That's 112, because there's 2 of those 56s. 112k plus 49. Let's just go ahead and write it as 48 plus 1 while we're at it. Yep. So this is equal to 8 times 8k squared plus, man, how many times does 8 go into 112? 14 times. Okay, so 14k plus 6 plus 1. Okay, so that's the completion of the fourth case. We've written it as 8 times something plus 1. I like to put in a final wrap-up. They don't necessarily do this in the book, I've noticed. But I like this, and I think it's probably a good idea. Since the cases are exhaustive, which is just a way to say that they cover all the possible values for odd numbers, mod 8, and in each case, our result was true, or the result held. There's a bunch of different ways you could phrase this wrap-up thing. It's something that kind of gives a final, puts a period at the end of the proof. Okay, maybe this is the period at the end of the proof. We'll put this colored in box there. All right, so you may have noticed that the algebra got a little bit ugly. Not horrible, but I would have preferred not to be dealing with like dividing 8 into 112. I, in fact, had to get a calculator for it, remember? So it would be nice if we could use either fewer cases or, find some other way to simplify things. So really what would be nice is if instead of mod 8, we could do this modulo something else. Now, it turns out that the most obvious thing is to use n mod 2. N mod 2, it's got to be 1 if you're an odd number, which is just really the idea of the even versus odd bit. That's not quite enough to get this result proved. So in between 8 and 2, there's a nice mediator 4. It turns out if you look at the proof of theorem 4.5.3, this is on page 206. You'll see they use the cases come from numbers of the values of n mod 4. And that's an improvement because we're going to either have n is of the form 4k plus 1 or of the form 4k plus 3. Because like we had in mod 8, if the remainder is 2, you're talking about an even number. And if the other remainder, or the other possibility is the remainder could be 0, and again, that's an even number. So if you're an odd number, mod 4, you'll have either remainder 1 or remainder 3. So that's something to always be looking for. If you've got a proof, and sometimes the most obvious version of cases is cumbersome, look for a smaller modulus or a smaller quotient remainder theorem instance that will let you get at the argument, get the same thing accomplished but with less work. So I ask you to look in the book that's on page 206 and compare the complexity of that proof with the one that I just did. The difficult thing about that is that you had to be clever enough to realize you could use mod 4 rather than mod 8. So a little flash of insight gets you that, and then you end up having to do less work. All right, last thing we're going to talk about is the triangle inequality. I'm not going to actually prove that for you, but the proof is in the book. It relies on a nice property of absolute values. I am going to talk about this property of absolute values. So given any real number, x, I feel like I shouldn't write a hash sign for the, what do you guys call it? Hashtag. The real name of that symbol is the octothorpe, but nobody wants to say that anymore. Let me just write out the word number instead. Given any real number x, there's a fairly simple inequality that involves x and its absolute value. And it's that it's less than or equal. And you can actually think about this pretty directly. If x is a positive number, then it's actually equal to its own absolute value. And if x is a negative number, and well, of course its absolute value will be a positive number. Absolute value is always going to be positive, so then this inequality would be true too. So that's a little division into cases thing. There's a third chunk of this that you might not always see, but it's also true that if you take the absolute value of x and throw a minus sign on it, the negative of the absolute value and the absolute value form a kind of a trap for x. It's got to be equal to one or the other of them. So you get that string of inequalities. So that gets used in proving the triangle inequality. And the way the triangle inequality is stated in the book, it's for absolute values. So let me just write it down for you. It says that the absolute value of a sum has to be smaller than the sum of the absolute values. The proof of this is on page 208. I just wanted to explain to you why they call it the triangle inequality, because the terminology is weird. I don't see any triangles naturally in this setting where you're talking about absolute values. So I've prepared some bits of colored paper that I can tack to the board with magnets. And so I've got the fairly long red line, and then blue line and a green line that are a little bit shorter. Now, as it stands, I don't have a triangle, but could I have a triangle? Yeah, if I turn these things so that the blue and the green Well, a little more than that, apparently. I can make a triangle with those guys. If this triangle was laid out in a straight line, you know, this guy would be the sum of x and y, but this is not in a straight line. Well, okay, so where's my scissors? I brought them out here, and then I put them somewhere. 1 second. I want to show you what happens if the other sides here are a little bit shorter than they were now. Say like that. Can I make a triangle with those 3 lengths? I get this red guy, and this blue guy, and this green guy, and yeah, well, okay, I kind of wish the blue was on top of the red, don't I? Even if I put them straight in a line, the sum of these guys isn't big enough to reach each other, right? So you don't ever get a triangle. So when these things actually are in a line like this, we need this third side to be smaller than the sum of x and y. The way I'm thinking of it is actually the sum of x and y has to be bigger than the other one. So when they're in a line like this, we could make a triangle provided this was true. It would be a degenerate triangle if it was just exactly equal. In other words, if this was equal, the red guy was at the length was x plus y, and that was equal to the length of x plus the length of y, we would have a triangle that could only exist if it was flat in the plane. But if there's some margin in there that x plus y is a little bit smaller than the sum of the other 2 guys, like, let me just cut it off, you know, pretend this part was removed. Now I can make an honest triangle out of it. And so how much the triangle becomes kind of fully 2-dimensional has to do with how far from that being an equality you have. If it's equal, the things are degenerate. You lie in a line. If it's unequal, you can form a triangle with these 3 lengths, x, y, and x plus y. Well, not quite. But that's the reason it's called the triangle inequality. It has to do with whether you could build a triangle having 2 of those sides being x and y. And the proof of it is pretty straightforward. They didn't mention trichotomy property at all in the proof, but I noticed them using it. The cases that they end up with are a number is 0, or it's positive, or it's negative. So look for that. Okay, so that brings us to the end of the lecture for section 4.5. It's almost 9 o'clock here. I hope I'll have it up on YouTube for you by about 10. So I know that's a bit late, but hopefully people will get a chance to look at it before tomorrow.